Today's industrial biotech is really based on scaling pharmaceutical biotech. So they're really specialized, targeted fermentation approaches that are really good for making complex, like drug molecules, but really bad for making the simple molecules that we need for fuel and food. So single, couple carbons linked together versus dozens and even 100 for pharmaceuticals. So when they started scaling those technologies, they had to use really expensive stainless steel. They had to use high temperature rated materials because the whole industry is based on steam sterilization, because you don't want to contaminate your reactors from one run to another over a week period. So what I saw working as a chemical engineer and taking courses was that wastewater treatment technologies use similar kinds of microbes and similar kinds of reactors, but they make them out of low-grade steel, cement, epoxy, plastic, really low-cost materials, and they're still able to get the kinds of conversions that other industrial biotech does. So when we were able to prove that we could use those kinds of low-cost capital equipment and still do our targeted fermentation, we knew we were onto something. Another problem we've seen with industrial biotech is that because they need to maintain sterile environments for their microbes to grow over these batch periods, they need food-grade sterile inputs. So they're using food ingredients like cane sugar, soy, and palm oil as inputs, which they have to then sterilize, but are also going to exacerbate the food ecosystem. So as these technologies continue to scale and become more impactful in society, what we don't know is how that's going to affect food prices in the future, or it's estimated currently that they'll actually need to deploy 5% more farmlands to support the entire industrial biotech industry if they're going to need these kinds of new inputs. So think a whole new state needs to get deployed of farmland, which is significant. Yeah, my scientific journey probably started quite early. Even as a Eagle Scout, I was really concerned about the environment and helping to make the world more sustainable, but ended up going to undergrad for doing chemical engineering, and for some reason went to a pharmaceutical plant, and the thing I really thought was interesting was their wastewater treatment plant. So that really kind of set me on a pathway on to where I am today, where I knew that biotechnology could really be the answer for sustainable problems today, and that natural biotechnology, so things like wastewater treatment, things that are operated at the millions of gallons of scale versus the thousands of gallons like in pharmaceuticals, for example, really were needed to get developed and scaled to bring to the market and bring big solutions to society. So ended up doing a PhD at Cornell, found a lab that was doing exactly that kind of fermentation, and thought we could develop something cool, and ended up spinning this tech out of my PhD. So a core reason why our fermentation works the way it does is because we do a practice called continuous chemical extraction. That's very different from how industrial biotech works today. So if you think about like making beer, you end up sterilizing your tank, you put the yeast in, you put all the sugars or all the malt in, and then you let it grow for a couple of weeks. And at the end of that batch period, those couple of weeks, what ends up happening is the microbes die because they produce so much product around them, so the ethanol, and they then can't produce anymore, and they have eaten all the food around them. So what microbes really are like machines connected to conveyor belts. And if the machine has enough food coming in on the input conveyor belt, it'll convert and make product. But if the product conveyor belt is full, which is what happens at the end of these beer brewing fermentations or industrial biotech fermentations, the bugs shut down. And what the industry then does is starts over, takes product out of that solution, and then restarts it. What Capro-X does is we essentially give that conveyor belt somewhere to go. So we do chemical extraction, all those products end up getting harvested out of the bioreactor, freeing up that conveyor belt for that microbe machine to just keep putting products on the belt, and then not be product inhibited. So taking food waste and making fuel or energy out of it is something we actually already do. Anaerobic digesters are today's best, most scalable fermentation solution for taking organic waste and making a biogas out of it. So it's methane gas you can then burn, make electricity. The problem has been that it's difficult to transport that stuff. You have to purify it, and they have the centralization issue where you need a lot of material to come in to refine to make it worth building a facility and trucking and centralizing into like a fuel facility. And other biotech industries like ethanol are already on the market, maybe with help from government subsidies and things. But with Capro-X, what we're able to do is actually upgrade those anaerobic digesters. So instead of having to build new bioreactors and all of our facilities, we can actually show up to places where they're already taking wastes and they've already figured out the input side of those organic waste materials. We can upgrade those biodigesters with our specialized extraction technologies and then lower the cost of deployment by like 40 or 50%. So that really helps with accelerating the adoption of our technology. But even as Capro-X is scaling and building systems on our own, our current cost to make meets an estimate by the Department of Energy to actually deploy sustainable aviation fuel without subsidies. So what they estimated was that if fatty acids from fermentation could be produced at like $50 a kilogram, so 25 cents a pound, something like that, you could actually use off-the-shelf oil and gas equipment, so things that already exist in the industry, and just drop off our chemicals and turn it into fuel. So the beachhead problem we're looking to solve, the real solution we're trying to deploy to the market, is to solve this waste problem from the dairy industry. When they're making cheese or Greek yogurt, every truckload of milk that comes in is essentially leaving 3/4 full of a byproduct or a waste that they have to dispose of on a daily basis and pay to get rid of it. So what we realized was that this wasn't just a local issue when we were at Cornell. This is an industry-wide issue. It's a national issue. It's a problem for every single dairy producer across the globe, from cheesemakers in Idaho to Ireland to New Zealand. So what we're able to do is deploy a much higher value market option for the dairy industry to take a waste that they used to dispose of or use as low-grade animal feed and then turn it into a much higher margin product that can get sold for a wide range of applications. Even applications they can use internally, like healthful animal feed, paper coatings, even plastic films for like the tops of yogurt containers. So our core product is this molecule called caproic acid. Today it comes from palm and coconut oil and ends up in market applications ranging from flavoring ingredients to beauty product building blocks to even plasticizers and even in some cases lubricants and fuels. Unfortunately, this particular molecule comes from unsustainable palm and coconut. And the issue with these two products is that they are responsible for a significant amount of greenhouse gases and also are related to the deforestation and the displacement of local ecosystems and animals living in those areas. So there's a lot of environmental disruption from these two industries, which has led to consumers and even major industries promising to divest out of palm. The concern right now is that while there has been a lot of promise, there hasn't been any real solutions that are scalable to market. So hopefully, as we keep scaling, Capro-X can be that key player that lets the industry transition away from those unsustainable inputs. But the opportunity is really out there for anyone to come in with anything that can replace palm or coconut. So interestingly, the oil and gas industry has this problem of too wide of a product. So you've seen these crazy complicated oil distillation facilities where they're taking oil and what you get off the top is gas. So you get like propane, things like that. You then get aviation fuel, then gasoline, diesel, and then asphalt, so like tar stuff. So the oil industry ends up having to deploy a portfolio because of nature that consists of like 20 different products. Differently for Capro-X, our fermentation really just makes 3 different products, 3 different fatty acids, which makes it much more simpler for us to commercialize our whole portfolio and not have to get rid of byproducts and wastes that these other industries done. So we are able to really focus on high value applications first that led us to scale, and then as we keep getting bigger and bigger and maybe little byproducts end up becoming truckloads at a time, we'll have to enter into those and enter new products into the market as well. But already the fatty acids we're making, our customers in the flavor fragrance space, for example, already are saying that our products are higher quality than what they're getting from palm because of some of the byproducts and the processing equipment that they're using today leave some off odors or off tastes in them that are really almost deal breakers for adopting those chemicals. So a lot of the times when we see these products on the market, it's a little yellow tinged. Ours is crystal clear, and we see that that's a value proposition we can deliver starting this year by using our fermentation tech. So my grand vision with Capro-X is that food waste is no longer considered a waste anymore, and really it's looked at as a feedstock and a valuable input for the bioeconomy. So as long as there's carbon and it's in a form that microbes can get to, which is basically any kind of food, ag, even a lot of industrial waste, that's carbon that's being landfilled or burned and really exacerbating the greenhouse gas impact issue. So if we can turn all that carbon from food production plants and corn facilities and sugar plant facilities and turn those into building block molecules, there's way more opportunities to take them into the bigger scales that we get.